Okay. So this is lecture 22, May 24th, 2021. Okay. So we started the topic of multi-degree of freedom systems by first showing how you formulate the equation of motion for a 2 degree of freedom system. So I'm going to do two simple example problems, but let me say this, that similar to single degree of freedom systems, this is what we are going to do. First, we will just do the formulation or deriving of equation of motion, okay? And then we show you the solution, okay? So that's what we do. Of course, in single degree of freedom system, we spend 3 weeks to model the system. We're not going to do that, because as far as the modeling of a multi-degree of freedom system is not as straightforward a task that we had in single degree, but rather we look at a few, systems that you can easily set up the model and then formulate the equation of motion. Then we show you how we solve the problem. So to do that, let's do two examples today based on the general derivation we did last time. The first example is a structural problem. The second one is a mechanical system, to be fair to everybody. So let's say you have a 2-story building. The weight of the 2 floors are given. The material and geometric uh, properties of the columns are given. So let's say this is E1, I1, L1, the length. This has a different length and different modulus of elasticity and so on. And there is no damping. So we want to set up the equation of motion. The way this building moves is that the connection between the floor and the columns are rigid. So no rotation takes place at this point of connection. So the motion would be like this, okay? So if this is U2, this is U1, no rotation. So of course, the objective is to find, these are 2 masses, right, moving. Find first the total stiffness that connects these 2. So the model that you are looking for would be something like this, that you have a stiffness between this and the floor, and you have another stiffness between the 2 floors, and you want to model the system like this. The way this system is moving, okay, is different from a cantilever beam. As I said, there is no rotation allowed at this point of connections. In a cantilever beam, when you had a displacement due to a load here, it moves like this, right? So you have both rotation and displacement. In this case, look at, for instance, here, what you have is an indeterminate structure. So you have a system that moves like this, that is rotation is 0, and you have only a displacement. So and you know that in order to find the stiffness, you need to relate force to displacement, right? Stiffness is the force that causes unit displacement. So let's look at a column that is subjected to a load and it is moving like this. And we want to relate this load to this displacement. We use, if you remember from the strength of material, you did this problem, but I'm just going to refresh your memories. You use the concept of superposition. You would say that if this is moving like this, the reason it's not rotating, experiencing a rotation, it is as if you have a load that obviously causes a displacement, delta 1, and a rotation, theta 1. But then you have an internal moment that is causing this displacement, total displacement, I'm sorry, total rotational displacement come to zero. Of course, this is causing a displacement on its own. So what you have in this superposition is the total angle of rotation is zero because there is no rotation takes place. Okay, and sum of these two displacement is the total displacement that we need in order to relate that to the force and find the stiffness. So that's the problem we have. We want to relate this total displacement to this force to find the, uh, the stiffness. So if you recall from the strength of material, and let me go maybe to another page, makes it easier. From the strength of material, you remember that if you had a load P causing a displacement delta 1 and rotation theta 1, delta 1 is PL cubed over 3 EI, okay? And theta 1 is PL squared over 2 EI. If you don't remember how you do this, just go back to Strength and Material book and look at the back of the book. There is a table actually for these. And for this guy, that is subjected to a moment, this theta 2, and this is delta 2. Delta 2 is ML over 2EI, and theta 2 is ML squared over EI. So we said that total displacement is delta due to this load, and this total deformation is zero. So theta 1 plus theta 2 is equal to zero. That means add these up, you get PL squared over 2EI plus ML squared over EI is equal to zero. So this will give us M is equal to PL over 2.
Professor,
Yes,
is theta the derivative of the deflection for the, is that the relationship?
correct. You know, this is how you did it, circular material. The equation, differential equation for displacement was this, okay? EI, or M is equal to EI y double prime, okay? So this was a second order differential equation. You derive the deflection. Yes, that is correct.
Okay, I was wondering for, correct me if I'm wrong, but theta 1, should there be a 2 in the denominator if it's the derivative of the deflection?
Oh, you mean the derivative of this?
Yeah,
No, no, no. You
okay,
you find theta 1 from that differential equation that you solved, not from here. Okay.
okay,
It is true that it should be, good observation, a lower order. This is L cubed, this should be L2. That you know. But this theta 1, your variable of integration is not delta or theta, is u is delta that you derive from that EI is equal to y double dot. But that, yeah, that's what it's gonna be. All right.
Did you just go over the theta 1 and theta 2? Because just looking at them, it seems that their units wouldn't be the same. Like one is a moment times L squared and the other is a force
The
times.
units should be the same. Units are the same because if you look at this, here you have, uh, let me double check though. Maybe I want to make sure that maybe you're right. I may have wrong um, values here. Let me double check. Good that you raised that problem. Let me double check that to be on the safe side. Okay. 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 Let's see. Okay. Let's see. Here we go. Delta 1 is PL cube over 3EI. Delta 2 is ML over 2EI. Delta 1 is PL2 over 2EI. This is ML squared over EI. So the unit, yes, should be the same. So what you're saying is this is pound foot, so it would be pound foot cube, and the unit don't match, right?
Yeah, well, just theta 1 and
That-
theta 2 are different, it seems.
Right. That you're right. Yeah, that's well, then, it's yeah, that's a good question. I have to see if this would be theta. Theta 1 is PL2. This should be ML. Yes, that should be ML. So looks like it. That would make it correct. Yeah, you're right. That should be ML because units otherwise don't match. So, so if you do this, but that this should come out to be PL over 2. So, yeah, that would be correct. That's correct. That's right. So you are right. This is PML. That's that. So this is going to be correct, right? Because EI and EI. Yeah, I'm glad you noticed that. So we corrected it. So that's what M is. So now let's write delta 1 plus delta 2 is equal to delta. Okay. So if you substitute those, you get PL cubed over 3 EI plus uh, substitute for M. So you have PL over 2 times L over 2 EI is equal to delta. And if you simplify this, a little bit of algebra, you see that delta comes out to be PL cubed over 12 EI. So we could relate now the displacement to the applied force, and therefore the stiffness, which is the force causing unit displacement, would be what? K would be 12 EI over L cubed. So for a column, or let's say for a beam, doesn't matter, that this end is constrained. So if it moves, no rotation is allowed. Okay. The stiffness is 12 EI over L cubed. Therefore, in the model that we set up for that structure, okay?
Professor,
Yes.
can I look at the deflection equations again, real
Uh-huh.
quick? For like delta 1 and delta 2.
Right.
Because I was comparing with my 207 equations sheet. I don't know if
Mhm,
you
mhm.
had it as ML squared over 2EI.
Oh, is it ML squared over 2EI? Right?
Yeah.
Yeah, so I had a unit. Yeah, I should have corrected that because I made a mistake here. So this should be ML because the units don't match. You're right. So this would be PL cubed from ML times uh, L squared over 2EI. And that's how, in fact, you get this PL cubed. So I'm glad that you guys corrected all these derivations today and I fixed them. So yeah, this is correct. So, but these should be fine. That's what it comes out to be. So what is this K here, which I called K1? This is the building. So K1 is the sum of these two because these two are moving the same, or in other words, you have springs in parallel. So K1 would be if 24 E1 I1 L1 cubed, and this K2 would be 24 E2 I2 over L2 cubed. Okay, so the equation of motion, we can set it up because if this is M1, this is M2, this is M1, you have this K U1, this would be K2 times U2 minus U1. For M2, you have just, this is K2 times U2 minus U1. And then you have the inertial force that we put it in the opposite direction. This is M1, U1 double dot. This is M2, U2 double dot. So these are the two free body diagrams. Write the equation of motion for each. You get M1, U1 double dot plus K1, U1 minus K2 times U2 minus U1 equal to 0. You have M2, U2 double dot plus K2 times U2 minus U1 is equal to 0. So here you did obtain the equation of motion for this two-story building. Any questions? So let me put a note here so that we did correct these. Okay. All right. No questions? All right. So we did a structural system. Now let's do another example of a mechanical system. And what a better example than a car. Okay. So this is the example that I want to do. Let's say you have a car. Okay. And center of gravity is somewhere here. So this car is traveling on a terrain and moving up and down and also rotating. The easiest and the most basic model that is used for uh, modeling a car as a 2 degree of freedom system is this simple model. We consider a rigid body, rigid beam. supported by two stiffness elements, which represent the tires, the shock absorber, all those. Let me call this K1, K2. So this is the center of gravity. So this car moves up and down and also rotates. So the center of gravity is moving this way, and also the car rotates. So we consider these as the 2 degrees of freedom. That is, the displacement shape for the car would be this. Okay. That it has both gone up. Let's say this, if this end has moved up a displacement of u2, this one d2, this one d1 also has rotated. So this is the angle u2. So this is the model, and we want to set up the equation of motion, and we use again free body diagram, the second law. So in other words, the free body diagram that we are considering would be this. You have this inertial force M1 U1 double dot. You have this inertial force, which is I U2 double dot. You have the force of this spring and the force of this spring. So this is the free body diagram of the car. You may say that this is such a simplistic model for a car, but believe me, this is a very basic model. Is the first fundamental model used even in some complicated analyses that you want to find simply the first two frequencies, and for instance, make sure the engine operation is not within that range or whatever that is a model that is used even in some complex analyses. I had a graduate student who did his thesis with me, and he worked on developing a sensor for measuring the tire pressure in real time as you were driving. It was a great thesis. In fact, we published it in a good journal. So if any of you are interested, that's the reward you get if you do the thesis with me. But anyway, that's the model he used. Very simple for developing, for setting up even his uh, artificial neural network that he employed for that problem. And if that means anything, but he's now working, he's a manager at Tesla. He only graduated 4 years ago, but he's a manager at Tesla. So that's a good source of motivation for doing this problem, right? Okay. I always have stories to tell. All right, so let's see how we are going to set up the equation of motion. So what I need to do is just set up the equilibrium equations, right? Summation of forces along y is equal to 0. What do I have here? I have m1 u1 double dot plus fk1 plus fk2 is equal to 0. Take summation of moment about the point of rotation, center of gravity. Summation of moment about O is equal to 0. Let's say in this direction. You end up with IU2 double dot plus, and by the way, I forgot to give you these dimensions. Let's say this, the distance from center of gravity to this end is L2, to this end is L1, and L1 plus L2 is a total L. So moment of this force about here would be Fk1 times L1, and here would be Fk2 times L2 is equal to 0. So these are the two equations. But how do we turn these two into equations of motion? we have a little bit of geometry to do, and um, because what we need, first of all, find FK1 and FK2, okay? And which is what? FK1 is what? The displacement that they have experienced, D1 and D2. So FK1 would be simply K1, D1, FK2 would be K2, D2. But our degrees of freedom are U1 and U2. So I need to relate D1 and D2 to that U1 and U2. In order to do that, let's look at the geometry of the problem. You have, this is the original position, right? So this is the displaced position. This is D2. This is D1. U1 is this. This is U1, right? And this is U2, okay? So you can easily, from this triangle, if you look at this triangle, right? What is this? This is D2 minus D1. So tangent of U2, which is the angles being small, U2 is what? D2 minus D1 divided by L, okay? Oh, actually, I reversed it. This is what I had called D1. This was D2, so I'm confusing you, right? So would be D1 minus D2, okay? So that's U2 and its relationship to D1 and U2, D2. Now, look at now this triangle, which is similar to this triangle. Let me label these. So A, B, C, D, E. So what I'm saying is that triangle B, C, D, okay, this triangle is similar to triangle A, C, E. So from the similarity of these two, I can write BD, okay, over AE is equal to this over this, L2 over L. But what is BD? BD is this length, is U1, D1, I'm sorry, BD is U1 minus D2, okay? This is U1 minus D2. How about AE? AE, AE is D1 minus D2. So let's substitute these into this equation. You get what? You get U1 minus D2 over D1 minus D2 is L2 over L. So this is another relationship between U1, U2, U1, U2, and D1 and D2. So you have two equations, two unknowns, meaning D1 and D2, that you want to find them in terms of D1 and D2. If you solve these two, you see that D2, in terms of U1 and U2, comes out to be, so I'm taking equation 1 and equation 2. 1 and 2, solve them for D1 and D2. D2 comes out to be U1 plus U2 L2. D1 comes out to be U1 minus U2 L2 plus U2 L. So I can simplify this, becomes U1 plus U2 times L minus L2, and this is L1. So U2, D1 becomes U1 plus U2 L1, D2 is U1 plus U2 L2. Substitute these into this equation for K1, for FK1 and FK2. If you do that, FK1 would be K times D1, which is U1 plus U2 L1. Okay. I'm sorry, L2 here. See, that's what it was. And FK2 comes out to be K2 times D2, which is U1 plus U2. Okay. I am making so many mistakes today. What's going on? It's only Monday. Okay. I'm glad that this time I corrected it myself. So by relating D1 and D2 to the 2 degrees of freedom, these are the two forces in the two springs. Now I need to substitute those into this equation, these two equations. Okay, so I just substitute these into those equations, and this is what is going. Once you do that, a little bit of algebra, you see that this is the equation that would result. M1 U1 double dot plus K1 plus K2 U1 plus K1 L1 minus K2 L2 times U2 is equal to 0. I U2 double dot plus K1 L1 minus K2 L2 U1 plus K1 L1 squared plus K2 L2 squared U2 is equal to 0. So this is the equation of motion for a car modeled as a rigid beam with 2 degrees of freedom. In other words, this is the equation of motion for this system, K1, K2. This is the center of gravity, U1 and U2. Any questions? No? Okay, if not, no, you have no questions, let's see where we are again. So we're talking about 2 degree of freedom systems, and for the time being, like single degree of freedom system, we are trying to just derive the equation of motion for the system. And as I said, we will cover two approaches. One is what you have seen in these two examples that I did, by simply setting up the free body diagram using the second law of mechanics, we derive the equation of motion. Similar to single degree of freedom system, also we want to introduce the energy method, because we found that energy method is a very powerful approach. In single degree of freedom, what we said was that if you can find the kinetic energy and the potential energy of the system, and the system is conservative, okay? Some of these two is always a constant, So by taking the time derivative of these two, which would be 0, setting up this equation, we could find the equation of motion. We will use the same concept of conservative systems, but instead of this approach, which also led to even Rayleigh's method, we use a different energy method introduced to us by Mr. Lagrange. Lagrange, if I'm not mistaken, was contemporary with, yet they lived the same era as Laplace, both famous, mathematician and physicists, French mathematicians and physicists. And they definitely made major fundamental contributions to both fields. In fact, Laplace did something that Mr. Newton could not even understand when it came to planetary motion. You know what Mr. Newton said? Why is it that the way planet, of course, in this case, our solar system, goes through an orbit which is elliptical, and how this motion, which is the orbital mechanics of this orbital motion, can be described? Why is it that they stay in that orbit? They don't collide with each other. What is the law of motion for those? Does anybody know what Mr. Newton said? How he discovered, seemingly answered that problem. And it was not until Laplace was the first person who challenged that and demonstrated what Newton had said was stupid. Anybody has read this story? No, apparently not, right? Newton come to that point, he said, the reason they stay in that orbit because the Almighty God has his way of doing things, and I cannot answer that question. They are there because God wants them to stay in that orbit. So Laplace actually discovered and established the orbital mechanics. He formulated and demonstrated why. So whenever we don't know things, right, we assume something beyond our control is the reason behind it. But anyway, so Lagrange came up with this idea. In fact, there's an interesting story behind it. He was traveling in a train, and which I will give you that problem. And he was doing some thinking, and he developed this mathematical formulation. But anyway, Laplace said, consider the same kinetic and potential energy. Instead of their summation, consider their difference. Okay? And then he proved something very interesting. He said if you have a system with multiple degrees of freedom, okay, let's call these Q1, Q2, whatever, Qn, you can demonstrate that if you take the partial derivative of this difference, which we call this Lagrangian. Okay. In fact, there's a whole field of Lagrangian dynamics. Now, if you take the partial derivative of Lagrangian with respect to each velocity of each degree of freedom, and then take the time derivative of that, subtract this term, which is the partial derivative of that Lagrangian, taken with respect to each displacement term, this is always 0, and this relationship will give you the equation of motion. You will see what a powerful approach this was through a simple example that I show you. But first, let me formulate what we need to do in order to use this approach, this energy method, Lagrangian approach. First, you need to establish or identify all the degrees of freedom, whatever the number might be. Two, set up kinetic energy and potential energy and find the Lagrangian. Okay? And then use this formulation and you will get the equation of motion. So let's demonstrate that through a very interesting, simple problem that you may have seen that actually even in physics or somewhere. It's a famous problem that the famous problem of the train. You have a train, there's a car, one of the cars in a train, and this train is traveling. So the connection between that train and others, I will sum it up as this is stiffness term. This train, the car has a mass, let's call that M1. And then, so in other words, this is traveling, and at some point it was here, now it is here. So the distance traveled is U1. And then we have a light fixture, okay, connected to the ceiling of this car. As the train moving this way, this is also moving. So in other words, you have a pendulum. And this pendulum is like this, okay? That it has a mass of M2. So it is going to rotate. So this represents a degree of freedom. So mass 1 has this degree of freedom U1, and mass 2 degree of freedom U2. Okay? So we want to set up the equation of motion. If you want to do this by using the second law, would be a tough problem. So let me redraw that because I want to show you and how we can simply do this using Lagrangian. So in other words, I'm exaggerating here. So this is the pendulum rotating this mass 2. This is its degree of freedom. This is that mass 1, U1. And I would set up this coordinate system here. This is X. This is Y. Okay. Let's say length of this pendulum is L. So this is basically also experiencing a translational displacement, and it is also experiencing a vertical displacement this way. So instead of dealing with U2, let's first look at this. Let's say that the displacement of this mass with respect to this reference frame is Zx, and with respect to this reference frame is Zy. Okay, so based on that geometry, I can now set up the kinetic and potential energy. What is the kinetic energy? Kinetic energy would be simply the kinetic energy of this guy, M1 U1 dot squared, plus, 1/2 M2 times the velocity squared, but this is moving in two different directions. So velocity this way and velocity this way. So it would be Zx dot squared plus Zy dot squared. But I want everything in terms of U1 and U2. So let's relate Zx and Zy to U1 and U2. Zx is what? Is U1 plus this distance, right? And what is that? If this is L, this is U2, right? This would be what? This is L sine of U2. So it would be U1 plus L sine U2. So Zx dot would be the derivative of this. So it would be U1 dot plus U2 dot L cosine of U2. U is a time variable, right? So the square of this is this, which is what I need for this term, right? But how about Zy? Zy would be simply what? This distance traveled, which is L cosine of U2. This is what? This is L cosine of U2. But since it is this way, I would consider that negative sign. So it's negative L cosine U2. Okay. So U2, Zy dot would be derivative of that, which would be L U2 dot sine U2, and the square would be this. So I would just substitute this and this into this equation. And if you do that and simplify this, a little bit of algebra, T would come out as 1/2 M1 U1 dot squared plus 1/2 M2 times all of these terms, which simplified, you get U1 dot squared plus L squared U2 dot squared plus 2L U1 dot U2 dot cosine U2. So this is kinetic energy. How about potential energy? That's easy. You have just potential energy of this mass, which is 1/2 K U1 dot. But how about for this pendulum? What is the potential energy of that pendulum? This is that pendulum, right? This is that mass 2 has gone from here to here. So the distance traveled, this is U2, this is L, is this, which is this one was what? Was L cosine U2. So this that we are looking for would be L minus L cosine U2. So this would be then mg, right, times L times 1 minus cosine of U2. Okay, so that's the kinetic energy. Now, as the next step, we need to set this up and then use Lagrangian formulation to derive the equation of motion, which is what I'm going to do next time. Okay, so you can see that as long as you can set up the kinetic and potential energy, not only can you derive, as you will see, the equation of motion, but we didn't even have to make those approximations of a small angle. You see that we have cosine term, we have the product of these, so we have a nonlinear equation. The general form of the equation of motion can be derived using Lagrangian. Of course, next time we'll simplify that, make it linear by making those assumptions that this angle U2 is small, so U1, which we assumed is MU2 which which we assumed was L sine U2 is actually L U2 and so on. We'll do that next time. But let's stop here and I'll see you during my office hours or on Wednesday. Any questions? No? Okay,
Thank
thank
you.
you. Have a great day. Thank you.
Do you have office hours?
Absolutely, yes. I'm going to have office hours starting right at 10:30. I'll see you there.